Is cyclohexane a nucleophile or an electrophile? I would say it's neither. We've got no lone pairs, we've got no leaving group, we've got no polarity really to speak of. It seems like we should never see cyclohexane or any other alkane engage in any reaction. But it can react, and it's actually a very industrially important kind of reaction. So if I take this thing and treat it with dibromine, the thick brown liquid dibromine, and I use light or heat, and I'll usually use light, and our shorthand for light is going to be this H nu. It looks like a V, but it's really the Greek letter nu. So H nu. But we'll give it bromine, a little bit of bromine, and a little bit of light. Actually, I guess one equivalent. And what I'll get is a brominated alkane. And actually, it might even keep going and give me bromines more or less kind of all the way around the ring, not in really any controlled way for this thing. So how does this reaction work? Where's my nucleophile? Where's my electrophile? It turns out that's not a great model for this mechanism. This mechanism goes by a radical mechanism, which works differently than any of the reactions that we've covered so far. Radical reactions have three kinds of steps. Three kinds of steps are in every radical mechanism. The first is an initiation step. So here, an initiation step, we're starting with no radicals and we're ending up with two radicals, where a radical is something with an unpaired electron. So here I'm taking dibromine, I'm giving it heat or light energy. That bromine-bromine bond is a pretty weak bond, and I'm just breaking it in half. Okay, so what the product of that are two bromine radicals. So again, we're used to breaking bonds in this class, but we almost always break a bond where both electrons in the bond go one direction or the other. That's not happening here. Here we're breaking a bond and half of it goes one way and half of it goes the other way. We'll call that homolysis, right? So cutting the same from the Greek. Our second step is propagation, and this is really the important step in any kind of radical mechanism. These are usually chain reactions, and so the propagation step is kind of the machinery that gives us our product, right? That kind of keeps the crank going. So for every initiation step, there are many, many, many propagation steps because it's a chain reaction. And so in this case, we've got this bromine radical that we made in our initiation step that can interact with this cyclohexane. And it's actually going to break this CH bond in half. And we'll call this hydrogen abstraction. We're abstracting a hydrogen. And so you can notice my arrows here. My arrows are fish hooks, right? So they're not like the normal double-headed arrow. Having the little fishhook arrow is the way we denote that only one electron is moving. So here my bromine is going to abstract my hydrogen atom, not a proton. This is not an acid-base reaction. Okay. And my product would be this radical, right? Again, I broke this bond in half, and HBr, right? HBr is where that Br ends up. Okay, so I have a new hydrogen-bromine bond. Now, this alkyl radical is now going to find another equivalent of bromine 2, right? So dibromine, our reagent up here. Okay, that's going to very quickly break that really weak bromine-bromine bond. So you can think of this as like a bromine abstraction or something, although that's weird. So you're going to make a new CBr bond, and you're going to leave another bromine radical. So this is my product, right? This is how I get that. But notice that as I form my product, I'm generating more bromine radical that's going to re-enter my chain reaction, right? So it's almost catalytic in that radical. So again, most of the products in a reaction are formed by this propagation step. What makes it a propagation step is that I'm starting with one radical and I'm ending with a different radical, right? This is also a propagation step. I'm starting with this alkyl radical, I'm ending with this bromine radical. And when I kind of end up with, start with one radical, end up with one radical, that's a propagation step. The third kind of step is a termination step, and that's where two radicals recombine. It's tempting to think of this as kind of the main way that we should get our product, right? That makes sense. You have some, maybe our cyclohexene radical and our bromine radical come together, and that's how we get HBr. But remember, at any point in time, there's only a very, very small number of these radical centers in our pot. Okay, and so it's not like it's just an entire flask full of radicals, and so it's very, very unlikely that two radicals are going to find each other, right? Most of the time, it's kind of like just finding that right person in this crazy, crazy world, right? Like, what are the chances that you find your soulmate? High enough, high enough. So, we want to keep our termination rates pretty low, because even though this is kind of an okay thing, I don't like this, right? Because this is just kind of the opposite of my initiation step, and I really don't like this, right? So if I have too many radicals in the pot, now I could have two cyclohexane radicals find each other and make a new carbon-carbon bond that for once I am not excited about. Okay, so I usually want to keep my termination rates low to avoid byproducts, to avoid side products like that. Okay, and one way I'm going to keep the termination low is to make sure my initiation rate is low. Right, as long as if my initiation rate is low, I've only got a few radical sites that are doing the work. Everything's going by this propagation chain that I understand and like, and termination really isn't mucking anything up. But if I have a lot of initiation, now I've got tons of radicals, and I'm doing some propagation, but I'm also doing a lot of termination, and that I don't want. This is going to become really, really important, this kind of thinking that I just talked about, next week when we talk about polymer chemistry, because most polymers are made by this kind of mechanism, and byproducts are really going to affect how good our polymer is. So, three kinds of steps for any radical reaction. Initiation gets you some radicals, propagation uses them productively, and termination destroys those radicals. And this is the important of those three steps.
What drives this reactivity if we don't have a strong nucleophile or a strong electrophile? What drives this reactivity is the difference in bond strength. So you are looking at average bond dissociation energies. So we talked about homolysis just now. So when I break these bonds in half, how much energy does it require to do that? So the higher the number, the stronger the bond, right? The lower the number, the less energy it takes for me to rip that bond in half. Okay. So for the reaction that we just saw, we started with a CH bond and a Br-Br bond, dibromine bond. And we ended up with an HBr bond and a CBr bond. So on a very, very rough sense, if we add up the bond dissociation energies that we started with, the CH and the Br-Br, and then we add up the bonds that we end with in green, you can kind of see that the bond dissociation energies in green sum to a higher number than the bond dissociation in blue, right? So in blue you end up with something like 600 or so, and in green you end up with something more like 630. And so we're trading weak bonds for strong bonds, and that's really the driving thermodynamic force for radical reactions. All right, the bromine-bromine bond is really, really weak. If I can trade that in and get even an HBr bond, that gives me quite a bit more stability. So that's going to be our driving process: weak bonds for strong bonds.
Hey, how does your refrigerator actually work? Right? Especially if you haven't taken physics in a while, you might not have thought about this. Your refrigerator works by having some volatile liquid that it can constantly compress and then let expand. Right? That's a big part of the innards of a refrigerator. And that's why the back is hot, right? And the inside is cold. And so to do that, we need some kind of liquid that has boiling point pretty close to room temperature, if not below. So for a long time, this was done by ammonia. Ammonia boils at, I want to say, -33, and so it's a pretty useful boiling point for this kind of thing. There's lots of problems with using ammonia in a refrigerator, though. A, it is flammable. So if there's a little bit of a leak and a spark can set it off, and now you've got a big explosion. And also, it just smells like ammonia, right? If you have a leak, it's that really pungent, awful amine smell. And so there's a lot of reasons why this was phased out relatively early on. This was replaced by chlorofluorocarbons. So there are lots of chlorofluorocarbons. What they have in common is that they are carbon molecules, usually 1, 2, perhaps 3 carbons, that just have fluorine and chlorine on them, no hydrogens. So there's pros and cons to this. The pros is that this solves all of our problems that ammonia had. It is odorless, it is non-toxic, and it is non-flammable. So if it leaks, it won't hurt you unless it completely displaces all the oxygen, and it won't catch fire, right? So, and the pro of that is that it's really stable, but the con is that it's really stable. This is a really stable molecule, and that's a good thing, but it's also a bad thing because it is lighter than air and it will evaporate. And as it goes up in the atmosphere, it doesn't break down, it doesn't break down, it doesn't break down, and until it gets up to into the ozone layer. So the ozone layer is what shields Earth from a lot of the UV light that comes from the sun. Once this makes it through a good part of that ozone layer and it's less shielded from UV light, now UV light can break that bond. So this would be an initiation step in some radical reaction. Right? So I'm definitely not breaking the CF bond, that's too strong, but I will break the CCl bond. Okay, so what? So I made some radicals. Well, now we're off to the races with a chain reaction. So here are three of several possible propagation steps that we can imagine here. So again, we're in the ozone layer. So these chlorine radicals are being generated in the presence of ozone. Ozone's O3. We'll end up with this ClO radical, which can then react with more ozone to get ClO2 here, which can now break down to give chlorine dot and oxygen. Now, just like your 7th grade math problems, we can cross out stuff that appears on the left and the right side to kind of get the overall net reaction. The overall net reaction here is that 2 molecules of ozone are being turned into 3 molecules of oxygen. And that's not good because we need our ozone layer. And so we needed to solve this problem. And we did so by essentially making something less stable. Right? The problem with this stuff wasn't that it broke down. Lots of things break down. The problem with CFCs is that they didn't break down until they got to the ozone layer where they could do damage. One solution is to use HCFC. So now if I've got a CH bond, these things can now break down much more readily well before they get to the ozone layer. So they're still safe enough for use in our hairspray cans and our refrigerators, but they're not going to chew up our ozone layer. But again, the problem here are these propagation steps, right? So once we generate any kind of radical, it's almost catalytic, right? It goes in a kind of an unstoppable chain reaction.